Welcome to Beyond Expectations, a podcast where we explore the ideas, people, and innovations shaping the government of tomorrow. No other public recognition exemplifies the best of government service like the Arthur Flemming Award. This podcast highlights recent Flemming Award recipients and the incredible work being done across government today. I am Wagish Bhartia, your host and Chief Growth Officer at REI Systems, a proud sponsor of the Flemming Awards. Today, I'm joined by Dr. Laura Sinclair, a physicist in the Fiber Sources and Applications Group at the National Institute of Standards and Technology, or NIST. She is also an adjunct professor in electrical engineering, computer, and energy engineering at the University of Colorado Boulder. Dr. Sinclair's work focuses on precision timing and frequency measurement, advancing the systems that underpin modern communications, navigation, and scientific research. Her research is helping extend ultra-precise timekeeping beyond controlled lab environments into real-world applications where reliability and scale are critical. Dr. Sinclair, thank you for being here.
You're welcome. It's a delight to have this conversation with you today.
Absolutely. So let's start off, kind of orient our listeners. As a recipient of the Arthur S. Flemming Award, please tell us a little bit more about your work at NIST and what you're focused on today.
Yeah, so here at NIST out in Boulder, Colorado, I serve as the project lead for the Optical Time Transfer project. And what we work on is using a very special kind of laser, a frequency comb laser, to transmit information about what time it is very precisely between clocks, when all that's between those clocks is just an open air path.
So for those of us that aren't experts on precision timing and or lasers, you talk a little bit more about why this research is so critical and what kind of got you into researching this topic.
Yeah, so when I say transmit information about time precisely, I'm talking about building systems that can link clocks that have 18 digits on the display. So that means if you had a clock display and I were transferring information about what time that clock was reading, you would have a clock that didn't have a second hand. It had a quadrillionth of a second hand in it. So they're incredibly precise instruments. We're measuring very small changes. And we do that with a very special tool. And a laser is a device that outputs light. Sometimes it outputs one single color of light that's very well behaved. And my laser is really special because instead of always outputting light, it only outputs it some of the time. We call that a pulsed laser. And it outputs many, many different colors of light. All of the colors we can control. They're very, very well behaved. And that lets me add that quadrillionth of a second hand to your clock. And because I'm worried about trillionths, quadrillionths, even thousands of quadrillions, I don't even know how to say that number of a second, we're really focused in our project on what's next. Not today's timing infrastructure, which NIST also supports along with USNO in the US, but really how far can we go? What are the limits the universe imposes on us in our ability to measure time and frequency? And I'm going to I'm going to pause and tell you one more thing. So we're so interested in measuring time that precisely, in part because we can. So frequencies and time are the quantities that we are best. We collectively, the people of Earth, are best at measuring. And what that means is we can use clocks, things that let us measure time and the rate clocks tick at frequency, to sense the world around us. We use them for timekeeping, right? To define the second. What does it mean when your second hand advances? Very important to places like NIST. But also we use timekeeping for navigation. So when you are trying to drive in Los Angeles and your phone says you have to move 5 lanes of traffic over to take the left-hand exit or get in the carpool lane, your phone is actually receiving timing signals from a global navigation satellite system, which in the US is GPS. And it's translating those timing signals into a position. And it can do it well enough now that it knows you are 5 lanes from where you need to be. And in less than a mile, you had better get over. And we want to advance our ability to measure where we are, not which lane of traffic are you in, but which width of the human hair are you sitting on? Are you 2 human hairs over? And and that might seem overly precise, but if we can measure position and height that well, we can say things about where does water flow? Um, why does it look like to a clock you're higher, even though if you used a laser level, they're at the same height? Well, it's because the clock actually is sensing how much stuff is underneath it. And so if we can measure very small height differences, we can say something about what's underneath. We can say something about how heights are changing, how the earth is shifting in its shape, which has big implications for our day-to-day lives.
That makes that's a great explanation. Curious how you were first exposed to this line of research and how you chose to pursue this from a career angle.
Yeah. So I sort of grew up in the world of physics and precision measurement. And in many ways, I ended up here courtesy of the Pasadena Public Library system. I grew up in California, and they've got a lot of nonfiction books and books on the space program. And I was really into the story of Apollo when I was a kid. So it's been fun to see the Artemis mission recently.
Yeah.
And that got me interested. And I got an undergraduate degree in physics. I got to work in a condensed matter lab at Caltech. It was super fun. I came to grad school out in Colorado. I worked on something sort of esoteric, which was seeing if electrons aren't quite round, if they're just a little bit out of round. But that time in graduate school out here in Colorado, I got exposed to the specialized tool, the frequency comb laser. And at the time, these were laboratory instruments. The one I worked with in grad school had advanced. It used to be to get it operating the right mode, we would hit them with little hammers and shake them and kind of jolt them into the right state. And the one I had in grad school was very advanced. It had a button you could push to jolt it into the right state instead of hitting it with a hammer.
Sure.
So you'd turn something on, you'd wait 2 hours for it to warm up, you'd jolt it with the little button, you'd turn some knobs, and you'd hope no one touched the temperature or the humidity in your lab. We had curtains around them to prevent dust, and then you could do your measurement. And I came to NIST first as a postdoc to work on the development of these frequency comb lasers. And in my early days here at NIST, a huge part of our effort was developing frequency comb lasers that could leave the laboratory, that didn't have something where you had to turn a little paddle for hours if the power restarted. And at the end of sort of my postdoc, as I was becoming a staff scientist here, we had some designs where if you lost the power to your laboratory and it came back on, the laser just came back on. And we added with my good colleague, JD Deschen, who's now affiliated with the University of Laval, we added a lot of modern digital signal processing control to these frequency comb lasers. We brought in modern electronics and ways we could control them. And we created something that was turnkey. And we demonstrated they could run inside the lab by we borrowed a fellow postdoc. His parents had a camper van and it had a generator in it. And so Marilyn Riker told her son, Greg Riker, who's now professor at the University of Colorado, Greg, you can borrow the camper van. And we thanked his parents in the paper, actually. And we loaded the laser into the camper van and we plugged it in. The camper van had this terrible generator in it, but it had power. And we drove around the NIST campus below the NIST speed limit and showed you could operate what had been a laboratory instrument that needed a beautiful optics laboratory in the back of a camper van, and it still worked. And that was the sort of moment where I was like, okay, we have this great tool and we don't have to be in the sub basement of the building to have it work.
Got it.
Which is pretty exciting.
Yeah, that's great. So, um, if you were able to educate the American public and the average citizen on the why the research you're doing in the work in NIST is so critical to their lives, are you able to offer a linkage either through your traffic and GPS related use case or others? I would say, hey, this is why this research matters and why it's leading to us to eventually better outcomes for the average citizen.
Yeah, so I would say generally, I work on what's next. So we have a lot of critical timing infrastructure, some of which the timescale group here at NIST supports. And that's today's standards, today's timing technology that's globally deployed. But what we know is that we don't know all the rules of the universe. We don't know how well we can do. So we're still trying to figure out what the rules of the universe are. So there's something called the standard model of physics, and astronomers and astrophysicists have looked out at the world and they've said, okay, it doesn't explain everything. We've got dark matter, we've got dark energy. Why is there not a bunch of antimatter here on Earth? And so we know there's some rules we don't have out there, and that what's next, this high performance timing and clockwork that we're working on here at NIST, lets us start to probe those rules. And once we know the rules, we know how to work between them. So, sort of the first reason is we just want to know what the rules are. We want to know what the universe has given us to play with, the same way that my colleagues in the past figured out the rules of quantum mechanics at a deep level. And now we have a lot of really cool new quantum technologies, things like quantum computing, really coming online. And the second answer is that today's technologies aren't enough in terms of the links. So when we look at what we can do, you can today make measurements at sort of a trillionth of a second, which is very small. But that's limited by our ability on a global scale to link the clocks. We're limited by the links between the clocks and not the clocks themselves. And we know that we could get more if we weren't limited by the links, but by the things at the end, the clocks themselves. And we know we could get more if we could measure faster. So in today's world, it takes a very long time to be able to see if your clocks are off by a trillionth of a second. It's not as quick as glancing at your watch hand. But with the technology I developed, it is as quick as looking at your watch to say, oh, your clocks disagree by a trillionth of a second. And what that means is we can take these systems, and in the future, if we could link them across continents through satellites, we could redefine the second. We could provide these ground rules of the universe, and we can start to measure things you just couldn't do before. No one would build a system that says, I have to be able to tell how I disagree in time at a trillionth of a second in only a second. You'd get laughed out of the room because there's no box you can go to the store and buy that does that. But if you can do that, you can start to do things like basically look at the technical term for it is the Earth's geoid. So you can think of this as the lumpiness of the Earth. So the matter under your feet changes how you feel the tug of that matter, how you feel gravity. The field for mapping this is called geodesy. And it's really important because it tells us things like, is there an oil field under my feet that I might want to try and extract oil from? Is there an aquifer under my feet? Is that being depleted? What's happening with this, volcanic field? There are parts of the world that are very hard using classical geodetics. So again, that mapping of the lumpiness techniques for like volcano fields in Alaska, islands, looking for how is water really going to flow? Are our models of where water is going to flow correct? Or is it going to be that moment where we lacked precision in understanding the lumpiness of the earth, and some places going to flood that we don't expect if we get a big rainfall? And so the long-term outcomes are going to be when we can take what now we're just trying to push the limits of what we can do to turn around and make these things so turnkey and so easy to use. They are a box you can go get off the shelf and say, yes, I can map my world at a centimeter of height difference. So I can start to check and say, hey, am I saying the right thing about that map of my geography? And to move forward.
Got it. Got it. No, that makes a lot of sense. I'm going to ask a two-part question that
Yeah.
extends what you are talking about. One is the negative case, or perhaps the sort of counterfactual that we take for granted around the precision of time and timing. And the other is the sort of up case, or sort of the futuristic possibilities that your research opens up. So on the first thread is talk a little bit about, if there were to be, I mean, we take for granted, I think, a lot of this now in the modern day. If there were to be drift or a lack of accuracy, how would that manifest in a meaningful way, sort of from a, NIST perspective, and perhaps then more broadly from a societal dynamic?
Yeah, so I want to start with grounding this in the fact that because I sort of work on what's next, I'm going to give you an answer that's more focused on today's infrastructure.
Okay.
Because the truth is, when you're pushing the limits of what's next, no one needs my timing yet. So if my level of timing fails and we drop back to sort of the current best you can do, you'll have some very, very sad PhD scientists and program managers, and some very, very sad graduate students who are getting pestered by their advisors, right?
Sure.
But it's not going to impact the average American citizen. Your life's going to go on the same way. And that's true even with today's current infrastructure. What to us here at NIST will seem like incredibly large changes, oh my goodness, something was uncontrolled and for a brief moment in time, we drifted off by a billionth of a second. You're like, wow, that was big. We should worry about that, right? That's not going to change where your cell phone says which lane you're in. These things build up over time. But those tools are in the back end, and they, as you point out, we take them for granted. So precision timekeeping with today's infrastructure is all over our lives. We use it for the power grid, to synchronize the power grid. We use it to navigate both in our personal lives, right? We use it, to help automate things like, ships and shipping channels. They're now, with the focus on autonomous navigation, right? This folds into, like, can you have a series of trucks that are driving themselves from a place with mining to where they need to go, and there's no operator, and they stay on the road. All of these sorts of things that rely on our cell phones, that 5G infrastructure that lets us stream cat videos whenever we want, relies on precision timekeeping at its heart, in terms of how the signals are processed, how things are linked up, who gets to go when. High-speed trading. So in the era of people on the stock floor calling things out, you had to timestamp things, but you only had to timestamp things as well as, the man in the corner, saying he wanted to trade. And now with computerized high-speed trading, all of those actions are timestamped. And that requires a time service, and that's reliable, that's viewed as, not biased towards one person or another. And that's pretty important, and it happens in the background. We don't see it. And this has been true for a long time, is that every time we've gotten an advance in timing technology, it's made our lives, I would say, better and interesting. And my favorite example is you go really far back in time and to the dawn of, navigation on the high seas. One of the huge challenges was knowing how far you were east or west. And there's this clock, Harrison's chronometer, and it's a big deal because you can't put a pendulum clock on a boat. It's sort of the old days version of my current problem, right? You couldn't put a frequency comb laser in a truck. And Harrison built a clock that could be started in Greenwich, and they made sure it read noon when it was noon in Greenwich, and they put it on the boat. And then in the middle of the Pacific, you could, when it was locally noon, you could see how far off you were from noon in Greenwich, and then you knew how far you were east and west, and you could figure out were you going to get to the island you were sailing to or not, or were you going to miss the port by, hundreds and hundreds of miles in the open ocean, no landmarks. And that really changed the world. And more recently, we have come to take for granted the navigational possibilities that come from having a pocket GPS receiver for pretty much most adults,
Yep.
And I mean, my watch, which gets a GPS signal, has more computing power than the Apollo computer, and it knows where I am better.
Yep.
And that system, when it was built, no one knew how much I think that it would get used and how many places would come to rely on that. And it just opened a lot of doors.
Yeah, no, that's a great point. The cascading innovation that explodes out of this type of research is not always predictable while the research is unfolding. So let's talk a little bit about that. If you were to look in a crystal ball and say, hey, we're able to get to the, 10 to the negative, what n number of precision, right? 18. Yeah, there you go. What possibilities does that unlock for us into the future, right? And you talked about unmanned vehicles and the whole constellation of things there. Perhaps it applies now with the return to space and exploration and perhaps beyond going forward. There may be a better understanding of the globe and the world around us. What are the 2 or 3 vectors that you would say, hey, these are possibilities and now could fall into place, much like you talked about navigation and GPS and all these things that came into place as we began to have a standard around the measurement of time more recently? What are those frontiers that you envision as possible?
Yeah. So there are a couple of different things out there. Because I grew up as a physicist, I'm going to tell you the one that's nearest and dearest to my heart first, even though it's the least practical. And that is, we make some measurements and we say, that's interesting. Because at some point, we're going to see something here on Earth that doesn't agree with that standard model. Something that says, ooh, we saw something that violates general relativity, or we saw, there's something else out there. Because we have all these measurements looking up at the sky that say there's something else out there. And here on Earth, we haven't turned up to something else. So far, everything we've measured in all our communities at the LHC, doing these various precision measurement tests here on the Earth, we've always seen things that are consistent with the standard model. And so I think there's potential as we push farther and farther into the future to have that moment where there's a new rule, a different thing out there. And then what people do with that, it's hard to say. Because it's so far, we don't know what it'll be out there. And so that's like the coolness factor for me in this. The more, I hate to say practical, but maybe the more immediate returns are sort of how you can use these optical clocks that are linked up, these clock networks. Sometimes we call them quantum sensor networks because they're tied to the fundamental physics of atoms, to sort of probe the world, and that can be navigation. So it can be things like you can maybe measure faster, you can not need as much of optical power to link up very long distances, and that might help you with deep space navigation. So it might help you know where you are if you have a spacecraft that's on a very long journey. They can't look back very often. They can only look back for a little while. You could have the ability to know where a cluster of satellites are relative to each other. So for me, I always think cluster of satellites is satellites that are all grouped together traveling around the Earth or somewhere. And a constellation is far apart satellites that sort of span the globe. And if you have a cluster of satellites, you've taken out the Earth's air when you link them up. And if you know exactly where they are relative to each other and you give them these very good timing references, You can use them to take pictures, looking up, looking down, at wavelengths, at colors we haven't been able to take pictures at before. And you can take basically long exposure pictures. The technical terms for that is a long integration time. But you get to open the shutter for a long time without the image getting blurry. And you get a new color you can look at that you maybe couldn't have looked at before. So you get additional piece of information. And that's pretty interesting. And then, there's sort of workhorse things, which is you can just do everything faster. So you might not care about having 18 digits, but you might really want to have 12 digits really, really fast. Because then you can have, because they're still bulky things, you can have a system that maybe can connect a lot of places. So you look for a second over here, you look for a second over here, you wait for the 5 minutes of the day it's not cloudy, and you send your communications and your timing signals ground to satellite. So maybe it's you don't have any more digits than you have today, but you can have those digits in just a few minutes. And so you can have some sort of master stations. I get asked a lot, am I going to have a laser in my cell phone? No, you are not going to have a laser terminal in your cell phone anytime soon. But you might have a master point the same way you have a cell tower, right? So the cell tower might have a laser station, and that might make things a lot easier than for everyone who's connecting to that cell tower.
Got it. Okay. I was hoping for lasers in my phone. I guess that's
It would be super cool. I really want to live with the flying cars and the, laser beams in my cell phone and I would like the transporter from Star Trek but some things it turns out physics says we can't do.
Got it. Okay. All right. At least for now. At least
for now.
Yeah. Got it. One of the themes that we've explored with some of your fellow awardees is how collaboration between agency A, agency B, between government and academia and government and industry plays a critical role to advancing some of the mission-driven outcomes we're trying to achieve through the work of our awardees. Do you want to speak a little bit? I know that academia may be a natural one, but there may be also industry intersections. Can you talk about how we take this and how these different parties all work together to advance your research?
Yeah, that's really critical for us because the problems we work on are really hard and they're big. And I professionally link things very, very precisely. And that means you also have to have linkages between people. I don't build optical clocks, but if I want to see how well I can link optical clocks, I need to work with people who build optical clocks. Thankfully, there are a lot of them here in Boulder. Sure. For an example of how we partner with our fellow Department of Commerce agencies, I'm part of a collaboration right now. We gave ourselves a fancy name. We call ourselves the Peaks to Plains Relativistic Redshift Collaboration. We're trying to use transportable clocks to measure height differences. And we're working with the National Geodetic Survey, which is housed over in NOAA. And one of the nice things here in Boulder is that part of the NGS laboratory is also here in Boulder. So it's very easy to work with them. Within NIST, I'm situated within the Communications Technology Laboratory. My colleagues who develop optical clocks in Boulder are part of the Physical Measurement Laboratory. They're a different part of the organization. And over in GILA, which is kind of its own special joint institute between NIST and the University of Colorado. And we all work together at that 18-digit level. And so that's sort of, a within Department of Commerce view of the world. Outside of that, with the frequency comb laser technology, one of the great things for me is as a new postdoc, young staff member, I worked on developing them. And eventually, we were able to transition a lot of that technology on. And there are several small U.S. companies that have, to be fair to them, poured millions of dollars of their own internal research and development money into building those frequency comb lasers up more and more, making them more robust. They have people who do cabling. And in turn, now I built optical timing systems. And inside those systems these days are commercial frequency comb lasers. So I no longer have to worry about, did I glue the little piezoelectric stretcher to the fiber just right, which took a lot of my time once. But I can go to an industry partner and say, will you sell me a commercial subcomponent? And for us, that was a huge success because it's a 18-digit precision measurement tool that now you can buy that works out of the lab. And that lets the field move forward. And it's really important to those of us who are here at NIST to see that work live on. So it's not just that we work on understanding the ground rules of science and working on what's next, but when we have a sense of maybe this is something useful for what's next, we are trying to do that tech transfer to see it go on to support the U.S. industry in our field because that's part of this mission.
Got it. Okay. That makes perfect sense. I wanted to conclude with talking about the Arthur S. Fleming Award and its intent to recognize individuals who work has lasting impact on public service. When you reflect on this recognition, two-part question. One, what do you think it says about the role of sort of frontier science in shaping society in the U.S.? And what guidance would you have for those that are following your footsteps, the graduate students or others who are sort of going through the process of saying, hey, I want to spend my life's work focused on frontier science? Can you comment a little bit on that?
Yeah. So the Fleming Award for me was really meaningful because it is that recognition of the fact that I am a civil servant and I'm doing this in service of all, our taxpayers to try and advance what's next to the point where we can really stay at the forefront, that we can develop, the standards of tomorrow, as well as maintaining those standards of today, things like our current critical timing infrastructure. So that had a lot of meaning to me that, someone recognized it's important to do this, to push that forward and to build that foundation. I think for the future grad students, going forward, there is a tremendous vitality to NIST in terms of their research. We work on lots of things, and we can work on things that are bigger, I think, in many ways than if you are in an academic lab. We have a lot of great academic partners. We've had great collaborations, but there's only so big most university labs can be. And NIST has just these resources that are amazing. I have my colleagues down the hall who have these transportable optical clocks. We have the hydrogen maser that's tied to the NIST timescale comes out of the wall in my laboratory. And if I want to know what's going on with the NIST timescale, I walk down the hall and I bug Jeff Sherman and I say, Jeff, how should I understand this? And it lets us tackle hard problems and sort of really push that forefront forward on things that aren't at the level where they're going to be tackled by industry. They're too new. They're different. No one knows what we're doing with them. But they're big and interesting.
Well, that's it. Many thanks to Dr. Laura Sinclair for sharing her perspective on precision timing, scientific innovation, and how this possibly manifests in each and every one of our lives moving forward. And many thanks to the teams behind the Flemming Awards and the National Academy of Public Administration for continuing to recognize leadership that strengthens public service through science and innovation.
Thank you for joining us on Beyond Expectations. This podcast series is sponsored by REI Systems. At REI, we are reimagining government together. Until next time, keep believing in the power of innovation and public service.